Oxidation-reduction reactions are quite common in synthesizing products in organic chemistry labs. While in general chemistry, oxidation and reduction reactions focus on circuits and moving electrons. In organic chemistry, the focus is on reactions of hydrocarbons gaining or losing bonds to oxygen and hydrogen atoms. The practice of oxidation and reduction reactions to synthesize products was used in this experiment to look at the distereometric ratio of a compound. Sodium borohydride was used for the reduction of 4-tert butylcyclohexanone to produce 4-tert butylcyclohexanol. HNMR was then used to find the cis and trans isomeric ratios of the product. The experimental procedure. 0.5 grams of 4-tert butylcyclohexanone solution and 4 milliliters of 95% ethanol was combined in a flask. 0.3 grams of sodium borohydride reagent and portions of 0.1 grams was added to that solution. The temperature was kept below 35 degrees Celsius as it was stirred for 15 minutes. After the 15 minutes, TLC analysis was performed. A TLC plate was prepared by drawing a straight line across a plate with 3 spots near the bottom, equidistant apart. Spot A was a reference spot of commercial 4-tert butylcyclohexanol. Spot B was a mixture of the reference end product, and Spot C was a sample of the product. The TLC plate was allowed to develop in a solvent of 75% ethyl acetate and 20% hexane. After the TLC plate developed, it was then dipped in p-N-acetaldehyde and heated on a hot plate in a fume hood. Spots appeared after a minute of heating and the results were analyzed. After the TLC was completed, the original reaction product was cooled and 6 milliliters of water was added, followed by 3 molar HCl. After the hydrogen gas ceased from being produced, the mixture was heated to a boiling point, then cooled to room temperature. The contents in the flask were transferred to a separatory funnel and the previous flask washed with 15 milliliters of diethyl ether and added to the mixture in the separatory funnel. The aqueous layer and the organic layer were separated into the 2 flasks. The aqueous layer was returned to the funnel and extracted with 10 milliliters of diethyl ether for a second time. The aqueous layer was once more removed and the 2 diethyl ether solutions were combined and washed with 10 milliliters of water. The aqueous layer was collected again and a final wash was completed with 10 milliliters of a brine solution. The diethyl ether solution was transferred to a separate flask, dried with magnesium sulfate, and filtered. The solvent was removed using a rotary evaporator and a final product was made. After the sample dried, the final mass was taken and HNMR analysis of the product and commercial 4-tert butylcyclohexanol was performed.
After we obtained the final product, we got a mass of 0.187 grams. Percent yield was calculated by taking our experimental yield, which was 0.187 grams, and dividing it by the theoretical yield, which was 0.468 grams, and multiplying it by 100. We got a 39.96% yield. This was the HNMR of our product. It shows both elements of cis and trans from the chair conformers. Around 3.7 to 4.1 ppm, we can observe 2 peaks with the integration values situated above. The integration values are simply the measurement of peaks that corresponds to the energy absorbed or released during a chemical shift. This implies that the cis and trans chemical shifts can be calculated to determine which type is most stable. The percentage of isomers can be used with these formulas. The percentage of cis isomers for our final product is 33.3%. The percentage of the industrial product cis isomers is 25%. The percentage of trans isomers of our final product is 66.6%, and the percentage of the industrial product trans isomers is 75%. Also, cis is more upfield in our experiment HNMR, which means it had a lower chemical shift. From all this information, we can conclude trans position is more stable. This is because of its position on the carbon-bearing hydroxyl group. The cis hydrogen is in equatorial position, but the trans hydrogen is in axial position, which means it is farthest away from the bulky hydroxyl group. Because it's farther away, the OH can attack better. Unfortunately, we had a systematic error during our experiment. Our NMR machine was displaying incorrect integration values. We couldn't do proper calculations with negative integration values, so we were instructed with new values.